So we start today's class. We're currently discussing the last problem from the electromagnetism worksheet, which apparently have some significant trouble. This question says, have a look over here. An magnetic field of flux density B makes an angle theta with a flat plane PQRS in as S42 and what is this? আচ্ছা এটা ভুলে এখানে চলে আসছে question number 42 এর নাম্বারটা somehow এখানে ঢুকে পড়ছে. It's not supposed to be here. Okay, my bad. As shown in figure 5.1. So here we have some magnetic flux density and the angle it makes with the surface theta. The plane PQRS has an area of A. State what is meant by magnetic field and especially in terms of A, B, and theta. The magnetic flux phi to the plane PQRS. So this would be phi equals to B into A. Sin theta. Yes! All right. Then it says a vertical aluminum window frame DEFG with width 52 centimeter and length 95 centimeter as shown in figure 5.1. So this is a certain aluminum window frame. Now this is what the problem is interesting. The frame is hinged along the vertical edge DG. So this is the side where it is hinged, which means this window can rotate about this DG line. Move around, rotate around. The horizontal component BH of the Earth's magnetic field is 1.8 × 10⁻⁵ Tesla. For the closest window, the frame is normal to the horizontal component BH. Now, this is the interesting part. Have a look. The horizontal component BH of the Earth's magnetic field is 1.8 × 10⁻⁵ Tesla. For the closed window, the frame is normal to the horizontal component BH. So when the window is closed, whatever the condition is currently, this is currently at 90 degree with Earth's magnetic fields, Earth's own magnetic field lines. The window is open so that the plane of the window rotates through 90 degree. So now we are gonna rotate the window through 90 degree and make it become aligned. From parallel with the Earth's magnetic field lines, we're gonna make it to become aligned with the Earth's magnetic field lines. Now the question says, explain why when the window is open, the change in magnetic flux linkage due to the vertical component of the Earth's magnetic field is 0. So the change in magnetic flux linkage due to the vertical component of Earth's magnetic field is 0. The vertical component of the Earth's magnetic field okay. আচ্ছা আচ্ছা এই পার্টটা আমি একটু তোমাদেরকে এঁকে দেখাই because it's important that you get a bit of a three-dimensional understanding for this part. Let me just show this to you. Let's say this is the aluminum frame. DGFE. Earth's magnetic field lines, let's say for the orientation of this location, because it let's say the Earth's magnetic field lines go through this aluminum frame window at some angle. Let's say let's say the Earth's magnetic field lines for this surface goes along this direction. There is a two direction of Earth's magnetic field lines B. Now, this is not perpendicular to the surface. So what I'm trying to show you is that, let's say if this was the phase view of this surface DGFE, then let's say Earth's magnetic field line is coming in at some angle like this. So I'm not trying to show you horizontal, I'm trying to show you at some angle, like a three-dimensional angle. So it's coming from left behind corner and getting into the surface, something like that. It's difficult to show in vectoring for paint. From this part, if you take the horizontal component of this thing, let's say at this point, if I try to draw the horizontal component, let's say the horizontal component is going to be in this direction, which is going to be perpendicular to the face of the surface, which is BH. And the vertical component of this B is going to be along this line, along DG. So let's say this is BV, vertical. So when the window is rotated about this hinge line, so it's going to be rotated around this line by a 90-degree angle, it is going to experience a change of the magnetic field line cutting through its BH part, not through the BV part, because BV is basically the vertical field lines through, I mean BV is the alignment of the magnetic fields, or BV is the component of the Earth's magnetic field lines to which the frame is parallel. So if you want to visualize multiple BVs, this will be vertical lines going up. The window is kept parallel with those field lines. Now, whenever we'll move this, for the duration of the move, it is these arms, DE and GF, will cut across those field lines. This will happen. This will definitely happen, because think about it. So if we have a lot of vertical field lines over here, let me just draw with blue. Blue is good. So this is the BV alignment. A lot of these are available in three-dimensional space. Whenever we'll rotate this window by 90 degree, then this D part will definitely cut across that those vertical magnetic field lines at 90-degree angle, and this FG part will also cut across those field lines at 90-degree angle. So let's say this is the possible new position of the window after 90-degree rotation. So DE and GF, they will produce exactly equal EMF because they are of equal length. Both of these parts will be cutting across the vertical magnetic field lines by equal speed. So the rate of change of flux would be exactly same for both of these side arms, and it will produce some magnetic field lines for the vertical component of BV. But DG will not experience any magnetic field, any EMF direction, any EMF generation, because it is practically remaining parallel with the field lines, and EF will also not experience any magnetic field, magnetic flux direction, because it is practically parallel with the vertical field lines. So up till this point, I have discussed about what kind of EMF should we expect this thing to produce because of the vertical component of the magnetic field lines. So D should produce an EMF, GF should also produce an EMF. Together they should produce double the EMF of one of them, and one side should one of these end, let's say EF end or DG end, can be negative, which we can try to find out. So I can try to find out in which direction. I mean, whenever it will start to move, we can try and find out what will be the direction of the current flow by Fleming's right-hand rule. Should we use right-hand rule? No, I mean, let's well, I can find out the direction. Direction to find kora decision একটু difficult হতে পারে, but it's possible. But I'm what can I say? I'm keeping it at hand for the time being, because that's not the primary problem of this question. We can essentially find out which side would be positive, which side would be negative by Fleming's right-hand rule, because it will be inducing EMF, but there will be equal EMF induced on either side of the D length and GF length. DG line and EF line will not experience any EMF produced because of the vertical component. It was a vertical component element. Now comes the horizontal component element. So this is the horizontal component. For the initial position, the horizontal component is perpendicular to the face of this thing. So currently you have the flux linkage across this coil for this orientation phi due to the horizontal component equals to B of horizontal component into A into sine 90, that is 1. So you have the maximum flux linkage. When the aluminum window will turn by 90 degree, this sine 90 will change to sine 0. So technically speaking, the flux linkage will change from maximum to 0 as the window will rotate through 90 degrees. So other than considering the length of the arms, just by looking at the surface, you can say that because of the movement of this whole thing, we're going to have some EMF produced across this coil, and the magnitude of this EMF can be given by EMF equals to minus d phi by dt, rate of change of flux linkage. So in this case, that d phi would be phi h minus 0, and over the duration of this thing, this quotient I believe gives us the duration. No, not so far. So it only gives us this thing. So there can be also another EMF induced across the face of this window because of this 90 degree rotation, because in this case the flux linkage relevant for the horizontal component of the horizontal component of the magnetic field is causing a measurable amount of change with respect to orientation. So two things. The vertical component is going to give us some EMF because field lines are practically cut, and we have some rate of change of field lines for the duration of the motion. And horizontal component is going to give us some EMF because of the change of magnetic flux linkage. Either of these things could be explained by the either mechanism or a similar mechanism, but I try to give the explanation. One, I'm giving you for the vertical component, I'm using the term of cutting, actual physical cutting for a wire or for a metal piece, because it's easier to visualize over here. And for the horizontal component, I'm trying to give you that the surface itself is becoming angled, so there is this change of magnetic flux linkage, because that's easier to visualize over here. So technically speaking, except for the DG length, so whenever the EMF will be produced for the horizontal component, I mean this entire surface will produce some EMF. So you cannot essentially give up / stop any part which is not under EMF. One thing we can say hypothetically is that if we consider the surface, let's say if we consider this whole thing as a single surface rather than 4 individual bar of aluminum, the whole rectangle as a single surface, which is responsible to produce the EMF, this whole thing will produce an EMF by its magnetic flux linkage variation, which we've seen in the earlier cases applicable for generator and other stuffs. How much voltage is available across the 2 points can be calculated by this thing, which is the EMF over here, and that comes through a lot of different variation. The problem of this question, I mean, the reason I'm discussing this question is because it goes further down and eventually becomes a bit complicated. So the question is to calculate for the window opening through an angle of 90 degrees the change in magnetic flux linkage. So you calculate this thing, how much of phi goes to BA. So that will be the maximum, and then eventually it will be 0. So BA minus 0. So this is the change in flux linkage. So Faraday's law of electromagnetic induction. You mentioned that. You know how to write this up. Then it says the window in B is opened in a time of 0.30 seconds. So this is what the time is coming by. That 90 degree rotation happened over a duration of 0.30 seconds. Use your answer in B2 to calculate the average EMF induced in the window frame. That's pretty simple. d phi by dt. You calculate the d phi, you are given the dt, you divide them, you get the EMF. Plus or minus in this case would not matter. So this part, workable, doable. So you find out the flux linkage, Weber, you by time, you get the voltage. Then comes the last section. It says, state the sides of the window frame between which this EMF is induced. State the sides of the window frame between which this EMF is induced. Now, there is a bit of a trouble. The trouble is that what this question is essentially proposing, that while we are going to move this thing for the duration of the movement, which of these two sides, maybe adjacent, maybe opposite, we don't know, if we connect a voltmeter across, will give us some voltmeter reading. If we connect a voltmeter across, will give us some voltmeter reading. Well, the key part that is important, that because of this whole rotation, we're gonna have an EMF generated across DG and EF. We're also gonna have an EMF generated across across DE and FE as well, because these parts are all connected by some this is a whole metal frame. So I mean, if you connect a voltmeter across just across D and E part, you're gonna get an EMF because of the cutting of this part. If you connect a voltmeter across, let's say, halfway of DG to halfway of EF, you're still gonna get that EMF value. So technically speaking, the measurable EMF would be available across the DG and EF part. This is the gross understanding because of the flux linkage variation. Both the D part and GF part will also produce some EMF because they are cutting across the vertical component of the magnetic field lines. That will also give us some EMF generation. So you cannot necessarily say that it will be only produced across DG versus EF, or it will be only produced versus D versus GF. All the three arms except for DG will be responsible to induce the EMF into this frame. This makes answer to this question pretty difficult to comprehend to begin with and answer as well. I mean, we could give multiple different answers and they might be correct for one set of aspect, they might be incorrect for another set of aspect. I mean, practically speaking, there is no answer that you can give in this question which can be wrong. Whatever you write will be correct, because all the individual phases would give you some voltage difference, maybe except for, only exclusively except for, if you connect a voltmeter across D and GF, because D would be cutting across the field line, vertical component of the field lines in the same rate as GF will be cutting across. So at any instant of time, the voltage produced by either of them would be exactly equal. Numerically, that voltage would be equal. So if you try to get a voltage difference across them, you're not going to get a voltage difference. But if you wonder, are they not practically experiencing EMF generation? Yes, they are experiencing EMF generation along their length by equal amount, which means if you connect them by some wire or using a voltmeter, that voltmeter reading would be zero because they'd be having the same value of EMF generated at any point of the motion with that 90-degree rotation. So in my opinion, except for this D and GF pair, any of the other pairing, adjacent or opposite, could be correct. I'm just trying to shoot. If you have a question, please raise your hand. We'll give you floor eventually. That helps. So that's just my understanding because that's how I perceive it. But what the CA people did, they did this. This question part was removed from the assessment. All candidates were awarded 1 mark. And then in examination report, they gave question discounted. Bam. Which is not a bad thing. But why would they do this? I don't know. Maybe this question does not necessarily set out for a assessment because there can be too many correct answers. But they could give all of those pairs in a column shape, but they didn't. They just discounted this question. I don't know why, but they did. So which is a bit of a weirdness. And that's why I wanted to discuss this whole thing in terms of the two different components of horizontal component of the and the vertical component both. Make some sense that both will be responsible to produce the EMF generation. Because this is one of those very few scenarios where your initial direction of the magnetic field lines are at some angle with the surface to begin with. For most of the other problems that you have done in your worksheet, and also if you go out for the later years compared to other than the problems given in this worksheet, if you go for the recent year questions, for most electromagnetic questions, you will find out that the electricity, that the alignment was initially vertical, and then we underwent some change. If you're talking about the change of those type, but that's not the case over here. We have the initial field line which is at some angle with the face of the rectangular frame, so which makes the problem a bit more interesting / complicated, which I believe needed some discussion. I'll take questions. Shubhra, bolo.
স্যার আমি ভার্টিক্যাল ফিল্ড লাইনের ব্যাপারটা বুঝলাম না স্যার। স্যার বি ডিরেকশন থেকে না ম্যাগনেটিক ফিল্ড আসতেছিল?
Yes.
তাহলে স্যার ভার্টিক্যাল ফিল্ড লাইনের ব্যাপারটা আসলো কোথা থেকে?
We have divided the B direction into two perpendicular components. One being the horizontal, which is parallel with the which is vertical onto the face of this thing, and BV is just vertically upwards, which is along the face, along the rectangular frame.
স্যার তাহলে মানে আপনি কি বললেন যে ডিই আর জিএফ পেয়ারটা আমরা কনসিডার করবো না বিকজ এই ভার্টিক্যাল ফিল্ড লাইন কাটিং হচ্ছে না?
Vertical field and cutting হচ্ছে, but at any point of time they will produce exactly equal amount of EMF because they will be cutting across the vertical component of the field lines at equal rate, so they'll produce exactly equal amount of EMF. So you will not have a measurable EMF or slash voltage difference across them because they'll be giving you the same value. So the difference of voltage across these two plates should be zero. They are producing
স্যার
EMF, but
বিএ
they're producing equal EMF at the same time instance.
বাট স্যার হরাইজন্টাল কম্পোনেন্টের জন্য কি জাস্ট অ্যাঙ্গেলটা চেঞ্জ হচ্ছে তাহলে?
Yeah, that's what I said.
সো অ্যাঙ্গেল চেঞ্জের সঙ্গে রেট অফ ইএমএফ চেঞ্জ হচ্ছে আর কি, রেট অফ ম্যাগনেটিক ফিল্ড লাইন কাটিং, ইয়া ওইটা চেঞ্জ হচ্ছে।
হ্যাঁ, পরেরটা যেটা বলছে ঠিক আছে, প্রথম যেটা বলছে সেটা ঠিক হয় না বিকজ ওটা লিখলে মার্কস কেটে দিবে। রেট অফ ইএমএফ চেঞ্জ ইজ নট আ টার্ম, বাট ইয়া, you got the idea.
স্যার আর হাউ ক্যান উই সে যে সাইন 90 থেকে সাইন 0 হলো?
Because the question says right over here that the window is open so that the plane window, that the plane of the window rotates to 90 degree. So the it says that the horizontal component BH of the Archimedes field is eto, for the closed window the frame is normal to the horizontal component. So when it was in this kind of condition to begin with, the horizontal component of the Archimedes field was perpendicular to the surface. As we opened it to 90 degree, then what should we expect to happen?
So sir, when it becomes exactly parallel at one after total rotation of 90 degree, like the plane becomes parallel to the magnetic field line, right?
For the
After
horizontal
it is
component,
rotated so 90 degree. Yeah,
for the horizontal component, yes.
yeah, for the horizontal components. Okay.
The vertical components would still be passing to the what is this thing called? No, to the window till point.
So স্যার ভার্টিক্যালের জন্য খালি ইএফ আর ডিজিতে প্রোডিউসড হচ্ছে, রাইট, ইএমএফটা?
Vertical জন্য we are having equal EMF produced across D and GF because D part and GF part are actually cutting across the vertical lines.
আর ইএফ তো হচ্ছে না বিকজ ইটস অলওয়েজ রিমেইনিং প্যারালাল।
Exactly. বুঝছো?
জি স্যার।
Alright.
স্যার সো লাস্টের জন্য আমরা অ্যানসার দিতে পারতাম ইএফ এন্ড ডিজি দুইটা।
I would appreciate that one as the most correct answer. I mean, if you connect a voltmeter across these two sides, you definitely get.
সবকিছু যখন স্যার ওরা হরাইজন্টালের মানে পার্সপেক্টিভ থেকে চিন্তা করে দিচ্ছে, সো
Well, the calculations were because the last question essentially tells us that state the size of the window frame between which the EMF is induced. So we are going to have an EMF induced across the whole thing. I mean, this is not essentially similar like what happens in a generator, because if you pick up one of the questions for the generator, let's say, আমার ভিডিও কার্ড ঝামেলা করা শুরু করছে রিসেন্টলি, মাঝে মাঝে ফ্লিকার করে, 1.5 সেকেন্ডের জন্য ডিসপ্লে অফ হয়ে যায় আবার অন হয়, কি একটা অত্যাচার। The PC doesn't shut down, by the way, only the display flickers. এই মোটরের কোশ্চেন একটাও নাই নাকি, আশ্চর্য। What is this?
স্যার এটা আমারও হয়,
কি
এটা আমারও হয়, লাইক দ্য ডিসপ্লে ফ্লিকার্স।
তো খুব ভালো জিনিস না, বা খুব মানে প্লেজেন্ট জিনিস না।
Yes, it is very irritating.
Sir, when you select problems to demonstrate here, do you just choose the most difficult one and annoying ones, or the ones that confuse you the most?
No, when I try to discuss the problems in class from my own choice for the portions that I have personally experienced, the students tend to have difficulties to understand, or even if they do understand the question, they miss a lot of marks in most cases while they are articulating their ideas. They have good understanding, but they have difficulties in expression. Either of these two things, or maybe combination of both. Those questions I prefer to discuss.
Okay, sir.
এই যে এটা মনে করো হচ্ছে আমাদের একটা generator. So এখানে আমাদের we had a magnetic field over here. We had some coil over here, and this question was that we are gonna rotate this coil at certain RPM or something like that. The coil is turned to an angle of 90 degree at a time of 0.14 second. So here, to begin with, initially the magnetic field was altogether parallel with the face of the coil. So initial magnetic flux linkage was perfectly zero. There was no magnetic flux linkage, but that's not the case for this question, because when the window was closed for the first position, the magnetic flux linkage due to the vertical component was zero because it was parallel with the fields, but the magnetic flux linkage for the horizontal component was maximum. So you had magnetic flux linkage for different magnetic flux linkage for two of these phases, but for these typical scenarios, initially there was only one component that is only one component is the horizontal component, which is parallel with the face of the rectangle / the coil, and there is practically no problem. But now we have. So that's how that question is unique. Arnab, did you understand the discussion? বুঝা গেছে কিনা?
Yes, sir.
Beautiful.
আচ্ছা স্যার,
বলো।
আমি একটা জিনিস বুঝতেছি না, মানে ওরা যখন স্যার আপনি কোশ্চেনটা আরেকবার একটু দেখান তো 49 এর
কোশ্চেন ক্লোজ করে ফেলছি আমি।
ওই জায়গায়
অ্যাপ্লিকেশন বুকলেট আলাপ করা শুরু করব। বলো তুমি, তারপর আমি শুনতেছি তোমার।
মানে ওরা তো স্যার মানে ডিরেকশনটা কি একবারে মেনশন করছে যে এমন ভাবে দিছে যেটা ভার্টিক্যাল আর হরাইজন্টাল হচ্ছে ইয়ে করতেছে, মানে দুইটা কম্পোনেন্ট, মানে হাউ উইল ইউ আন্ডারস্ট্যান্ড যে কোথায় কোথায় আর কি দুইটা কম্পোনেন্টে ডিভাইড করতে হবে বেসিক্যালি?
You wouldn't. I assume that. They said that the window is in the closed condition of the window was only normal to the horizontal component of the magnetic field, Earth's magnetic field. So I assume
ও আচ্ছা,
it will not be perpendicular to the vertical component. That's why I consider
আলাদা করে যখন বলছে হরাইজন্টালের কথা আর কি
to be not perpendicular to the face of the window.
স্যার
বলো।
স্যার এই ম্যাগনেটিজমের ভার্সিটিতে কয়েকটা প্রবলেম ছিল, ওটা কি বলবো?
ক্লাসের পরে বলো, আমি কিছুটা পড়ায় নেই, তারপর আবার নিব না, সমস্যা নেই।
আচ্ছা ঠিক আছে।
আচ্ছা, in our last class we were discussing up to this point. We discussed up to this equation. This is the piezoelectric this is not piezoelectric, this is the specific acoustic impedance of a physical medium, which it gives us a bit of an idea that how much fraction of an incoming intensity of a wave, in this case ultrasound, it is will be reflected off a boundary. So IR is the reflected intensity, I is the total incident intensity. So if you do the subtraction of these two, you're gonna have the transmitted intensity, which is not a part of this equation, but the basic subtraction can give us the transmitted intensity. And then this ray is gonna start penetrating through the second medium, and this is gonna start give us some interesting happening as the incident ray goes through a certain thickness of medium. Now there is a catch. The catch is we are in this case, well, whenever any wave, mechanical or electromagnetic, I mean, other than laser, laser is actually specially designed to not to get scattered. It goes in a perfectly straight line. It does not become dispersed away. It's made in such manner to maintain its intensity in a single straight line. It doesn't spread out. But just a second. All right. Salam. The thickness. So whenever we send any light intensity, any wave towards a direction, whether it's a mechanical wave or an electromagnetic wave, waves always become attenuated. Attenuated means they lose energy as they cover distance. This loss of energy is characterized by two factors. First factor is that waves spread up as they travel from one point to further. The second point is that waves lose their energy whenever they actually travel through a physical medium. The medium particles absorb portions of the energy, so it does not remain in the same form. So one of the very simple example that's very easy to understand is if you try to think about the propagation of sound through a physical medium, let's say through air medium, if you want to consider, when sound, ultrasound or normal sound doesn't matter, when sound travels through gaseous medium like an air, it essentially causes the medium to undergo compressions and rarefactions, which means the primary form of energy that makes it sound wave is vibration / kinetic energy. So if I make a sound out of my mouth, it will be spread out in the three-dimensional spatial direction. So as you go further away, the intensity will decrease. And this is a given because the same amount of energy will be now disturbing bigger number of particles because they are further away from my mouth and part of a much bigger spherical shape. So that's one thing, that's the spreading out. The second thing is that even if it is spreading out in this manner, beyond a certain point, the sound will be altogether undetectable, because as the air particles will vibrate, they are gonna rub against each other. So there'll be some internal friction that will convert that kinetic energy of the sound into heat energy, basic heat energy. So there's a difference. So initially you had when the sound was available, you had a disciplined vibration that was passing through the medium, and soon after this disciplined vibration is dissipated as heat energy into the atmospheric particles. So it's no longer sound energy. So two things, one is spreading out, the other one is absorption due to the presence of the particles, physical molecules in the medium. These two factors will reduce the intensity of a signal as it travels from the source further down. And this incident of reducing the intensity of the signal is what we call attenuation. The more it travels, the more attenuated it becomes. This traveling essentially is applicable for in the forward or in the backward direction as well. What I'm trying to mean is this, that let's say if I make a sound from one boundary and the sound is supposed to hit a wall and come back to me, for the echo to reach to me, think about it, for the echo to reach to me, that sound wave has to travel the in-between distance twice. It has to go forward to the wall, then bounce off the wall and reach back to me. So in this process, that sound wave, will attenuated by the same medium twice. As it is getting forward, there'll be one amount of attenuation because of the forward motion, where the length of the medium is the distance from me to the wall. And then as the sound wave is going to come back from the wall to me, that same medium will do a second attenuation of equal magnitude. Because technically speaking, for the echo to reach to me, it simply has to cover the distance that is double compared to the distance of me and the wall. So that's a pretty important factor, which will come very important for our some calculation further down the line. Now, we have the so this is the equation that is given up to us, that if we send an incident intensity of I naught at the beginning of a medium, it means the intensity of the incident wave which is entering this block of material, which is the thickness of x, the entering intensity is I naught, and as it will travel through a thickness of x, finally at the end point of the medium, the intensity would be I equals to I naught e to the power minus kx. So this equation, this fraction that you can see into e to the power minus kx is basically very much similar like the decay equation of atomic phase that you've come across, a equals to a naught e to the power minus lambda t. Here it is I equals to I naught e to the power minus kx. So this is a negative exponential relationship, which means the further it has to travel, the reduction of intensity will be exponentially dropping down, where k is the constant for the medium, referred to as the absorption coefficient. So there is an interesting thing that for ultrasound, this equation, this constant k is defined as absorption coefficient, whereas this exactly similar equation for the ultrasound, for the x-rays, where we have the same shape of equation, I goes to I to the minus mu x, where in this case the mu is called the attenuation coefficient or absorption coefficient. So have a look that for the ultrasound they're calling it the absorption coefficient. For x-ray they're calling it the attenuation coefficient or absorption coefficient, linear absorption coefficient or linear attenuation coefficient. So you practically can use any of these terms. I mean, this does not have to be given as a different letter of k and mu. You could use alpha, beta, gamma, any of these letters for your preference, because it's not a fixed letter like other constants. This is just medium dependent constants, so you could use any letter to represent this attenuation coefficient, but it has the name of absorption coefficient or attenuation coefficient. For the case of X-ray, we use the new word linear. I don't know the significance of the naming differences, so I'll not take time for that. Sorry. Here we can see a sample table for the absorption coefficient for different medium that we can have. We have air, water, muscle, bone. You can see the absorption coefficient can be significantly different. You can see that air has an absorption coefficient of 120, which means whenever ultrasound will travel through air, it is for every meter of air medium, it is gonna have an absorption coefficient of 120. So 120 per meter. Now I could go ahead and try to define what this quantity is in terms of SI unit and everything, but they didn't do this in our syllabus, so we don't have to bother this. The way with the maths are gonna work, which I'm gonna show you from some examples from the worksheet, is that they're going to give us some values, and we simply have to be able to use the values for the appropriate equations in appropriate cases with appropriate logic. So what does that mean? Coming up. So two things that we have to take away from here. One thing is that whenever, let me just draw this up for the wrapping. For the wrap, let me just draw this. I'm continuously hachi batse. I'm continuously choke and nak bolte se class nitese, and trying to figure out that exactly at which point of time I have to mute the channel so that your ears are not blasted into oblivion. কিছু বুঝলা?
Jason.
So I'm going to draw up a figure over here, and there will be some hypothetical divisions. Let's say this is the medium that we're handling, that we are dealing with. And I mean, other than giving you this discussion directly, I might as well get you to the question that which has this problem and give you this explanation, which will be easier for you to understand. আচ্ছা, এখানে এই পর্যন্ত আমরা মনে রাখি and it relevant একটা problem অনেকগুলো প্রবলেম আছে আমাদের একটা প্রবলেম আছে which is really unique স্টুডেন্টের প্রবলেম নিয়ে অনেক ঝামেলা পড়ে because there is a squaring thing and why does the squaring thing happen students to understand this less, so I'll explain this in the relevant question. I mean normally কে দেখাতে গেছিলাম but it's easier to understand if you see the question first, so I'll do it then. So this part of this discussion that I was about to show you is for the time remaining paused. Here we have a simple ultrasound scan image, intensity versus distance image for a skull or a head scan. If you wondered that why would someone do an ultrasound scan for the head, well, whatever reasons that they did, and we apparently have a view like this. I'm having intermittent signal breakdown in my monitor every 30 seconds or so. This is becoming extremely annoying to take a class. Why is it that technical stuff go? So কয়দিন আগে আমার ইলেকট্রিসিটি লাইনে ঝামেলা হয়ে ডাবল ভোল্টেজ হয়ে আমার পিএসইউ পুড়ে গেছে। আমি নতুন পিএসইউ লাগাইছি, I had to change the keyboard to a mechanical one. কত 3 সপ্তাহ 2 সপ্তাহ না 3 সপ্তাহ হয়েছে, and then now we have this problem. I'm just keeping quiet because I'm looking at the flickering of the screen. You guys have no idea what is happening because you're not receiving it, because you're seeing the output through a LAN wire or the Ethernet cable. So you have no idea what is happening in my screen, but I am bedazzled by this thing.
It's the problem with the monitor, right, sir?
No, I connected this monitor to another laptop output. It worked just fine. I assumed that it was a problem from the power connection, so I changed the input power adapter for the monitor. It still is the same problem. Then I googled some stuffs and they told me that there might be some issue with the graphics card, the GPU, for the intermittent flickering. So I updated the graphics card. I did some bit of a cleanup from my C drive for virtual memory space and everything. Nothing helped. It just flickers. My game is totally blasted out of the way because I cannot do any type of gaming out of this thing because I have to play in real time. I mean, I don't have view for 2 seconds, means I'm practically dead. Positions where I could save my teammate, I cannot anymore. I could save myself, I cannot save myself. So I'm practically feeding and overfeeding, and my teammates are giving me knocks and kicks. Beautiful life. So I'll just try to talk through it by having my eyes closed because it's too much disturbance. So if you're raising hand, I have no clue that you're doing this. So keep it shut for the time being. I'll eventually look at the participant list and give you floor if you have any question. So what is happening over here, that in this place, this is actually a linear representation of the intensity that is detected by the ultrasound probe when it is sent from one side of the head and as it travels through the head and eventually bounced off. What you should be seeing that there initially at the very left of this figure, let me zoom in a little bit. At the very left, we have a really large spike. This large spike is the transmission pulse. So we are producing the ultrasound pulse of this much intensity. This intensity of ultrasound pulse is produced at the piezoelectric transducer, or at the piezoelectric crystal, the silica crystal, which is operated by the machine. This sound pulse is going to come out to the plastic cover of the probe, which I showed you the earlier class, and eventually is going to travel through the gel coupling medium and enter into the skull. So try to think about it. Whenever it will enter into the skull, assuming that there is no hair, unless we have shaved off the hair because it's physically possible, and if you're trying to make ultrasound scan for the skull, it's very recommended that you shave off some of the hair because that's simply going to add noise to your analysis or data collection process. So whenever the ultrasound will enter into the hair, the first medium change is going to experience is as it enters into the scalp. Scalp happens to be the skin of the skull. So the bone is the skull. The skin layer above the skull is the scalp. So it's going to enter into the scalp. So there will be a first medium change. So there will be a bit of a reflection from that medium change. It's going to travel through the scalp thickness and then it is going to hit the skull. That skull happens to be the bone, which is a very hard medium, which has a very larger density, and it's a very strong reflector. So it will produce a very strong reflection, which is shown as the second large spike over here. So this one. So this is the scalp echo. This is the skull echo, and then it's going to travel through the skull thickness or the bone thickness, and it's going to then hit the entry boundary or the first boundary of the brain, actual brain. So the third pulse that you can see, that is coming off from the brain. So we are having three medium changes over here. First, the sound is entering the scalp. Then from scalp, it is entering the skull. Then from the skull, it is entering the brain. So three medium changes giving you three different echoes depending upon their individual specific acoustic impedances. You are having different intensities. The harder material skull is giving you a very large intensity of reflection. Then the ultrasound is traveling to the head normally. Human head has a crease or incision. Is called median fissure. Yeah, fissure. It has a crease at the middle, which it makes apparently look that the centrum has two parts, but it's actually not two parts. It's just a crease that is in the middle. So like a gate barrier reef or something like that. No, not gate barrier reef. It's just a crease at the middle. So it's not two different parts. It's just they both are joined at the bottom. So it's a single part, but it has apparently two different. There's an incision. It's still very much brain, but there are just two parts of the brain connected to the. For example, let's say if you just join two parts of your hand together. So I should be normally saying that there is hand and there is hand. There is nothing in between, although there might be some air particle trapped in between, although they might so happen, but in the brain there is no air particle. It's an enclosed cavity. So because of the median fissure, there is a bit of an incision. From that part, we're gonna get a bit of reflection. So that midline deflection is why he's telling us that where the median fissure is. So you have to understand that we are measuring all of these individual intensities, which are the reflected intensities from that location, and in this case, this graph is plotted with respect to time-based calibrated as distance, which means we know the typical speed of ultrasound through this medium, the head, for example. So we can measure very precisely how much time it takes for each of these pulses to be received, and then we plotted with using the time information, using the speed information, and the time that we have measured after which each of these echoes were received. We converted that time information of the echo reception into distances from the source. So that's what this time is. Time is calibrated as distance because it is possible as long as the speed of the ultrasound is same, or at least considered to be same for all the medium. It might not as well be same. You have to understand that different acoustic impedances. I mean, skull is a bone structure. It should have much significant higher speed of sound because it's a more strong solid, so it should be able to transfer the vibrations more faster. And then brain is a sloshy thing, brain kind of thing. You know how it is. I don't know how the proper adjective define the structure of a brain. It's soft, mushy kind of thing. So it is liquidish but not liquid essentially. So it will have a different speed of sound. So what we can do other than using an average speed, which will be more important, that if we know the individual speed of the sound, ultrasound through each of these individual medium, if you wonder how do we know that, well, scientists can do repeated experiments to find out these values with significant accuracy values. It's possible. It takes time and a lot of human effort and good equipments as well, but it's not impossible to find out. But once you find out those values to a acceptable number of accuracy, you can use those values for all the upcoming or further coming investigations. So that basically is a very beautiful thing. You don't have to do this for every individual patient. You can have a general value for those materials. So we are using the time information and converting the time information with using the speed of the sound in that specific medium in terms of distance. That's why this graph is basically intensity on the y-axis and distance on the x-axis. That distance is measured / converted from the time gap from the point of sending the signal to the point of receiving the signal. So we are having this much distance from the skull to the median field, which means this is half the brain. So this actually tells us that how thick this person's brain is for half, up to half. Now, then the sun can travel further, and the same thing that will happen over here is going to happen right up over here. It is supposed to, and it will happen, and then this will come back all the way to over here. So one of these transmission pulse is giving us all of these individual spikes for a healthy brain, for a regular brain. Now, there are multiple things that I would like to discuss about this figure. First of all, before I tell you the possible discussions for what is happening in the variations of this figure, I'd like to take questions that if you have any questions up till this point. So in the participant list, I have Abias raised his hand. Yes, Abias, go ahead. You have a question?
Sir, that was from a bit earlier. I was going to talk about like the absorption coefficient.
Yeah, sure, you can. No big deal. I'll take questions for the whole part that I didn't take questions for.
Sir, like, is the principle same for the X-rays and the ultrasound, no matter what?
Yes.
Like, how much it can penetrate through a certain material?
Yeah, the reduction of intensity of a signal for a wave. In generally, for all the waves, the attenuation due to the thickness of the material is expressed by the same equation. Now, depending upon the type of wave that you're handling and the type of medium that you're dealing with, you can have different values of that mu. For X-rays, you're going to have one type of values. For example, let's say human flesh. X-rays will have one value for human flesh, whereas ultrasound will have a different values for human flesh. So, depending upon the type of wave that you choose, you're going to have different values for that mu or k, but the core equation remains the same.
Okay, sir. And another one involving intensity time graph.
Yes, go ahead.
Like, how is the image really created? I understood how it works. I understood how an image is formed from voxels and X-rays, but here it's more difficult to imagine. So, like,
you're asking about the CT scan part, right?
yeah, I understand how it makes an entire image, but not when it comes to ultrasound and a intensity time graph.
Oh, you're asking me how this thing converted into an image?
Yes, sir.
Yeah, I'll explain this. I didn't explain this yet, but I will. It will come up in the later part of the discussion. Fine.
আচ্ছা স্যার
আচ্ছা ফাইন এক সেকেন্ড বাবা একটু দাঁড়া হ্যাঁ বলো
আচ্ছা স্যার স্কাল ইকোসের ওই মাঝখানের লাইনটা মানে একটু বেশি লম্বা কেন অন্য দুইটার চেয়ে?
কারণ প্রথম এইটা যেটা এই কোটা হচ্ছে স্ক্যাল্প থেকে মানে হচ্ছে মাথার যে চামড়া ওইটা থেকে দিস ইজ এ সফট টিস্যু এরপরে হচ্ছে বোন থেকে মাথার যে খুলি দ্যাটস এ হার্ড টিস্যু তারপরে হচ্ছে ব্রেনের বাউন্ডারি থেকে হুইচ ইজ ওয়ান্স এগেন এ সফট টিস্যু সো হার্ডার বাউন্ডারিজ গিভস ইউ স্ট্রঙ্গার রিফ্লেকশন
Oh yeah, thank you sir.
Sure. শুভ্র
স্যার ইনিশিয়ালি যখন ট্রান্সমিশন পাস দিছে পিজোইলেকট্রিক মানে ক্রিস্টালটা তখন স্যার মানে ও তো আসলে রিফ্লেকশন রিসিভ করতেছে রাইট
ইয়েস
স্যার প্রথম যে ট্রান্সমিশন পাস হলো ওইটার রিফ্লেকশন কিভাবে রিসিভ করলো তাহলে
that transmission pulse can be added artificially from the machine at t equals to 0. It doesn't necessarily receive that transmission pulse. It actually feeds it to the system, and you can add that transmission pulse artificially into your graph in your computer software. It does not detect that; it sends that out.
আর স্যার আগের পার্ট থেকে একটা কোশ্চেন ছিল সেটা হচ্ছে বেসিক্যালি we can say that the intensity is reducing due to a reduction in the kinetic energy of the sound waves, right?
Energy being dissipated out as heat and also the energy getting spreading out. Two factors.
Like kinetic energy থেকে অন্য কিছুতে কনভার্টেড হচ্ছে আর কি বেসিক্যালি।
এটা হচ্ছে heat conversion আর এটা হচ্ছে spreading out, which means that the same amount of kinetic energy is now responsible to vibrate bigger number of particles. So you're having distributing.
Spreading out is basically like the intensity becomes weaker because মানে particular place focus থাকে না the wave. Is it like that?
It's not about it's difficult for me to comprehend in terms of focus. Is that if you are close to the source, let's say if the source is producing, if the source has a let's say power of let's say 1 watt, close to the source, that 1 joule of energy released in 1 second will be vibrating a certain number of particles. But as you go further away, that same amount of joule would be distributed in a bigger number of particles because the wave is going to spread out. Then if you go even further away from the source every single second or fraction of a second, the further you go away from the source, that wave front would be distributed over a bigger number of particles. So 1 joule remains 1 joule, but now distributed across a bigger number of particles. So per particle, you have a much smaller amount of energy available.
জি স্যার বুঝতে পেরেছি।
Beautiful. So there are certain changes that this figure should have, and which the software actually does this correction. And what kind of change, what kind of variations should this have? I'm gonna show this to you to make some changes. So I'm gonna take this picture out onto here. Okay. So bear with me, and if you have any question, keep your hands raised. And for the time, please drop your hands. It helps. Fine. Do you have any further question?
No, sir, I forgot to lower the hand. Sorry.
It's all right. So the other thing is that এখানে Shubhra, I'm waiting. Do you have any further question? Shubhra, do you have any further question? All right. Never mind. So one of the key things that you have to understand that whenever the sound, you can see over here that in this figure, the size, I'm using size to represent the y-axis value. Let's say I'm using a different color to be red. The size of these echoes are pretty much identical to the size of these echoes. But if you think logically, is it supposed to be equal? Think about it. This skull echo has apparently the same amount of intensity as this skull echo, but are these two skull echoes to begin with should be of equal intensity? Should they be? One is produced close to the probe, the other one is produced on the further end of the skull. So they are not supposed to be equal. So if you plot the actual intensity received by the probe, you are definitely going to have this part to be significantly squashed. For example, something like this. On the further side, the same medium is going to give you much smaller reflection. And these small intensity variations, if plotted with the real values, can become too small for the people to be able to see, or in your printed out information or in your printed out graph can become too small. The machine is able to detect that, but the value of those things would be decreasing exponentially, which means they can prove to be extremely small. So might as well add to might as well add difficulties in terms of observation. So the software is tuned to take up these small intensities and increase their representing values to human observable value so that it looks easier to analyze. So practically the intensity of the further end reflection is not same as the closer end reflection. It cannot be, because though these sound waves had to travel through the entire length of the brain and eventually came back. So these reflections cannot have the same intensity as the close reflections. They will be definitely smaller. Artificially, they are made to be taller, so that they're more visible / easier to analyze for the people who are using the graph for the diagnosis of the patient. That's one thing. The second thing is that this is how a regular graph looks like. If a person does not, a regular person's regular human being, or a healthy brain looks like. I'm gonna make this thing come back to original shape. If a person has some anomaly in their brain, let's say if a person had a stroke, and in a certain part of his brain, he now has a bit of blood clot. That's the stroke idea of stroke, that you have some blood getting clogged in some part of your veins or arteries, which causes the problem. So that would mean places where we are supposed to have uniform distribution, we're going to have a significant amount of, for example, if you consider the skull, so this is the skull, and this is the skull, and this is the scalp, figure not down to scale. This is the median facial human brain. Okay, and let's say if we place the probe over here and we're sending ultrasound pulse over here, so we're having all of these individual reflections which are seen over here. Let's say if a person did undergo some stroke, and let's say we have a blood clot right over here, which is significantly large, this should give us another reflection in a place like this, which is supposed to be the anomaly, because this blood clot, which has a significant shape, would be providing a different change of medium. So other than regular brain material, you'll have a change happening from the starting end of the blood clot to the end point of the blood clot. So if you have a blood clot like this, actually I did a wrong drawing, is that other than having a single spike, you are actually going to have two spikes. On the entry boundary of this blood clot, you're going to have one spike, and on the leaving boundary of this blood clot, you're going to have another spike. The gap of these two spikes can give you a precise information of how big the blood clot is, and this much distance can tell you exactly where in one-dimensional distance, how far is it from the probe. So this is the distance from the boundary to the location of this thing, and this much can tell you how big is that problem or anomaly. Not essentially blood clot, it can be also applicable for tumor, if some person has some brain tumor, or if there is some physical object that got inside the brain somehow. More applicable for war times, if someone gets bullets or stuff or sharpness entered into the skull. They are still conscious and alive, which means that it's not affecting their active part of the brain, but that it can still be inside the brain and cause subsequent damages to the person. So it's possible for us to detect anomalies into the brain by doing this scan. So this is basically what we're looking for, or this kind of information is what we're looking for when we're doing the scan. So how does this linear information, you have to understand that each of the pulses that we get out of this thing are all linear information. So how can we use this linear information to convert it into a three-dimensional image, or into at least a two-dimensional image? The idea is, let's say we do one scan of a head from one location. So we have one of these lines. So we now know that along this line, this is the distribution of the medium. If we move this probe a little bit, let's say now the probe is over here. Might as well draw this with blue maybe, let's say. Now the probe is placed over here, and we do the same scan through a similar or a bit different line. So this is going to give us another line where we should have a similar type of behavior. So each of these individual pulses will give us one linear information for the reflection path. The device or the piezoelectric crystal can be vibrated thousands of times per second with this each individual transmission pulse, which means this ultrasound pulse can produce thousands of linear scans back and forth every second. Actually, it can be more than 1,000. I forgot the number, but it's a very high number. It can do a lot of scans every second because it is only sending one pulse, waiting for the pulse to come back, and then it will send the second pulse and waiting for the pulse to come back, and it will keep on doing this through the head and collecting information. We can line up all of this information from different places of the brain, and the spatial position where the spatial location where the probe was placed, and the data that we are receiving from the reflection of this probe, we can combine these data in a software to produce a three-dimensional projection of the human brain. That if this is the human brain, we can do the scan in all of this part. I mean, let's say I'm doing the whole scan on a significant portion of the left side of the brain, and aiming the aiming the ultrasound probe in all the appropriate places. So I can actually scan the entire brain in a lot of alignments like this, like let's maybe millions of alignments, and all of those elements are going to give me this kind of graphs, which are still going to be slightly different from each other. So it's very much similar like what happens for our vision, that whenever we see an object's three-dimensional view, both of our eyes detect a slightly different version of that image, and whenever they overlap in our brain, we get the three-dimensional feel. That's basically exactly what is happening over here. By placing this probe in different places, we get linear information along that line for each individual send, pulse, and scan. And later, all of these things are combined together in a software to give us the three-dimensional view inside that person's brain. So typically speaking, so whenever an ultrasound scan is done, for example, let's say for a human head, it's pretty difficult to find in the internet. I tried that a bit earlier, but I was not very successful finding it in the internet for the ultrasound scan for a human brain. But it's very, very common to find for a baby. So let me pick up one of those pictures. So let's say this is the ultrasound scan of a baby boy. So the reason we have this kind of a U-shaped, or because it's like a bit curved conical shaped thing, is that you have to understand that this is the line through which the probe was moving. This boundary basically represents the backbone of the mother. So we are sending one pulse through here. We are getting all the boundaries. We are storing the information. One pulse through here. So, and we are sending multiple pulses towards the backbone, and we are making it move through the whole thing, and we are getting all the individual linear data of this thing, and eventually, ultimately, we are obtaining that this is the type of behavior that we have. So every single time the ultrasound pulse is traveling through different medium changes, it gives us a variation of intensity, and those intensities are plotted in a black and white image. You can see over here, they have given us a scale over here. This scale usually have some units, but what this scale essentially tells us that the thicker the material, the whiter it is. You can see over here that for this kid, the backbone is pretty grown up. You can see there is more white over here, and over here that the skull is also pretty grown up, and then the nose and other stuffs, these are quite thick materials, where the hands and the legs and the lungs, these are not really go well. For example, the entire chest cavity is not really that developed for this kid yet. So they have this kind of, and locations where we don't have any type of media, for example, these are the amniotic fluids that we have and the baby. So these parts are just representing basic void space, which are black, which means that we didn't have much of reflection from here. And then this part represents maybe the uterus wall and the pay muscles and the fat tissues of the mother, so which have also some amount of white color. So stronger reflections are represented by more white, and weaker reflections or zero reflections are represented by black. This black and white image, based upon the intensity received, gives us the whole scanned view of an unborn baby, something like this. So the machine basically measures the intensity of these things, and based upon the strength of the intensity, it assigns color in a two-dimensional image, and that color variation basically tells us what's inside that thing. So that's the best I can explain, but I'll take questions right now if you have more questions. Yes. Yeah, Shubro, go ahead. No, not you. Shubro, you didn't drop your hand, so you make a practice to drop your hand. It actually helps. Abias.
So is this a single 2D slice through a single plane?
No. What this thing is, the software has a lot of different sectional views for the kid. For example, try to think about it. Let's say the mother is pregnant, and we are moving this probe all over the lower belly where the kid is located. So, but we are not having, say, the PC has access to information for all the individual sections. It shows us a section, or in the printed form, we get the sectional view that has the most variation of intensities, or that would be supposed to be most interesting to us. For example, whenever we are making one level, if you think, try to imagine, not in a realistic sense. Let's say pregnant mother is frozen. I'm not saying killed, just to make sense. And if you try to think of multiple cross-sectional slices, you will have to understand that there'll be certain locations where there is no baby, and then there is a bit of baby, then there's a bit of fingers of the baby and the forehead of the baby, then there comes the skull. So if you think of multiple cross-sections, there are individual layers of the whole thing. So the software has information for all of the locations in a linear direction. It's not like individual slice or cross sections like the CT scan or MRI. So now we're going to go for MRI as well. Rather, it is linear information in all directions. So the computer shows us typically in the printed report the alignment of the body or one sectional view of the along the womb that has the most variation of intensities, or that is most interesting for us, or the technician / doctor can actually choose from different alignment views that which alignment gives us the best information for what we are trying to scan for.
So, sir, is the probe moved in a crisscross grid pattern?
Yeah.
And from that, highest variation readings, they combine to form an image.
Yes, precisely.
Okay, sir.
পোলাপান বাকি যারা শুনতেছো বুঝা গেছে কি হইতেছে এখানে?
স্যার রিডিংটা তো মানে when constructing the image আমরা তো প্রত্যেকটা ওরিয়েন্টেশনের থেকে ডেটা কালেক্ট করছি, কিন্তু do you mean যে জাস্ট কন্ট্রাস্টটা ডেভেলপ করার জন্য যেখানে সবচেয়ে বেশি মানে ইজিলি ডিস্টিংগুইশ করা যাবে ওই লোকেশনটা ইউজ করা হচ্ছে?
Yes. For example, if you try to give a bit of an idea, for example, let's say whenever an ultrasound is going on, you have to understand that the baby does not know that he is being videotaped. So the baby is not essentially holding steady, baby is moving. But in this ultrasound, we cannot have a moving blurred picture of baby because we don't want that blurred picture. Rather, we would like to have a pretty stationary picture. So we have the instantaneous data for all of these different alignments, which you can stack up in our convenient way that gives us the best diagnosis image. বুঝা গেছে?
Yes, sir, understood.
Sure. So this is the last part for this whole thing. I would like all of you kids to read a certain paragraph from this part, which I'm going to zoom in, and I would like you to ask me questions if you have any from this part. So I can make it available. Yes. আচ্ছা দাঁড়াও। আচ্ছা এখান থেকে পড়ে আসো, এইটুকু পর্যন্ত পড়ো, তারপর আমি আবার নামাই দিব কারণ বি স্ক্যানটা আবার পড়া আগে এইটুকু পড়ো। Thirty seconds. All right. Any question about this thing? This is about one scan of one pulse. Then on the lower paragraph, we're going to combine all of these scans, which is going to call the B scan. But এইটুকুর মধ্যে কোনো question আছে কিনা? Anyone?
আর ইকোর ব্যাপারটা একটু এক্সপ্লেন করেন তো।
ইকোর কোন ব্যাপারটা? This whole thing is what
Compensate for this, the letter and echo is
this meant for this image. Whenever I showed that this part is gonna be is supposed to be smaller, the actual received for the distant part of the echoes are gonna be actually smaller. So the farther late an echo is received, it is amplified more on the display to be more visible.
আচ্ছা।
Anything else? No. B scanটা বড়, এটু বড়। Zoom in a bit. আচ্ছা, মাল্টিপল ক্রিস্টালের পার্টটা আমি বলতে ভুলে গেছিলাম, এটা আমি একটু পরে বলতেছি, বাট পড়ে যাও, পড়ে শেষ করো, তারপর মাল্টিপল ক্রিস্টালের পার্টটা আমি বলতেছি। All right, I'll take questions. Before I take questions, I'll discuss this part. So let me just go in the drawing board and show you some part. What the multiple crystal thing is about is that, let me select this, make it large, and try to explain. It's actually not. Acha. The thing is, in an actual probe, let's say this is the probe. This is a probe. In an actual probe, we usually don't have only one piezoelectric crystal. We have multiple piezoelectric crystals aimed in different directions. So let's say this is aiming in this direction, or this is aiming in a bit different direction. So they can be either concave or they can be convex, depending upon the device. And each of these individual crystals will send out slightly different frequency of ultrasound so that they would not overlap, and they will be detecting that exact frequency. So other than taking a lot of time by using only one single piezoelectric crystal to take a lot of images and eventually completing the whole image, the probe can have a lot of crystals which are aimed at slightly different angle from each other, so that we can make multiple scans using the probe at the same time, using slightly different frequencies for each of these individual piezoelectric crystals. So that basically speeds up the process of a whole huge number of A scans. Those can be later merged together to produce the two-dimensional image. So the idea of B-scan is simply that we're going to have quite a good number of crystals which are oriented slightly differently to get slightly different alignment to the patient's body. And we're going to do A scans using all of those individual crystals, which is going to speed up the process of scan for the data collection. That's basically it. বুঝছো কি বলছে?
Sir, what is basically the A scan?
A scan is the scan of one single piezoelectric crystal to give us a linear view like this. One single pulse sent out from one P crystal, producing one pulse-based image like this. And B scan is a lot of them overlapped onto each other to give us the two-dimensional image.
Sir, why two-dimensional? It should be three-dimensional, right?
The software can hold the information as three-dimensional, but whenever we print it on a piece of paper, we basically print it on a piece of paper, so it becomes two-dimensional. B-scanner part বুঝে গেছে সবাই clearly? More people are leaving from the class, so yeah, understandable. But for those who are still with me, বুঝে গেছে কিনা?
তো স্যার এতগুলা ক্রিস্টাল থাকলে হাউ তারা ওভারল্যাপ করে না, মানে টাইম পিরিয়ড তো তারপরও উই ক্যানট প্রডিউস, মানে একটু হলেও একটা ইন্টারফিয়ারেন্স হওয়ার চান্স থাকে না?
Interference হওয়ার chance থাকে, but the thing is, I mean, here's the deal. Let me put it this way. The devices that we use to detect the voltage variation of the across the crystal will have some latency, or let's say some reaction time or some lag. To make a complete scan or a perfectly understandable scan, what do we have to do? We have to first use the crystal to produce a pulse, then stop the sending pulse and wait for the reflections to come by, and allow the whole reflections to come and detect all of the voltages individually. And then once the process is done, then we should energize this a second time. So the gap between in consecutive send pulse will be something. Other than that, if you have, let's say, two crystals placed side by side, for example, consider only two crystals, where let's say the first crystal is operated at 22 kilohertz, the second one is operated at 25 kilohertz. They have a bit different frequency, and they're aimed at a different alignment. They will overlap at a certain position inside the brain if they are concave, if they're convex. But if they're concave, they will not overlap. They will simply go out in opposite directions and immediately come back. They will, I mean, we are trying to, here's the deal, you have to understand that we are trying, by the A scan, we are trying to detect the reflection intensities along a straight line from the crystal through the patient's body back in the same line. So whenever we use different frequencies, the superposition of these waves are minimal, because to have a significant superposition, we need to have all the waves to be coherent. So whenever we use slightly different frequencies, which is not said over here, I'm just telling you about the different frequencies a bit further into the line, because I want you to understand it properly, that whenever we use slightly different frequency for all the individual piezoelectric crystals, all of them can send their pulses with very short time delays, compensating for the lag of a single crystal's voltage measurement mechanism. Let's say the electronic component, which is responsible to measure the voltage across the piezoelectric crystal to be able to detect the individual pulses, that has some latency. But if you use two different crystals, you can measure another pulse within that time. I mean, the time duration for within which a crystal is being ready for the second pulse, you might be able to make another scan with the B crystal, with the second crystal. And other than having only two of them, if you have, let's say, tens of them or hundreds of them, and they are sequenced in a proper manner, you can have simultaneous scans with very small time delay variation through using all of them, and you can get multiple variations. So this is basically like the way I can tell you is basically like how can I say? Let's say.
So we are utilizing the latency as well as adjusting the time period.
Exactly. Adjusting for the time period so that we can gather more information within a short period of time, so that the patient doesn't have to be on the diagnosis table for a longer period of time.
Yes, sir.
Beautiful. Thank you.
Sir, what did you mean by latency here? Like,
latency usually means lag or ping, or the delay between between receiving something and detecting something. For example, let's say basic idea of human reaction time. Let's say if I touch a hot object onto the skin of my hand, how long would it take for my brain to detect that there is warmth in my skin from the incident where the object was actually touched on my skin? There is a bit of a gap, because the physical electrochemical signals have to travel through my nerve endings and eventually go to my brain, and the brain has to process this information as a heat sensation. So from the incident of that happening to the point of understanding what is happening is what is called latency.
yes, sir.
Good. So that's pretty much about the ultrasound scan. The last thing that we have, আচ্ছা এখানে আমাদের কিছু problem দেখাবো. And here we have a certain graph. This graph is actually pretty interesting, and it's very much like the graph for radioactivity chapter. What they're trying to show us over here, that for a specific medium, there lies a certain thickness of the material which causes the intensity of the transmission. This is for this equation, not for the reflection, to reduce by half. So if you're sending a signal of 100 intensity, if whenever it will go through this amount of thickness, the remaining intensity would be 50%. And if it goes to another amount of this amount of thickness, the remaining intensity will become half of that, and then half of that, half of that. So the thickness of material which reduces the incoming intensity by exactly half is called the HVT, or half value thickness. It's given over here. This definition comes in the question, so it's important definition. The thickness of the medium required to reduce the transmit intensity to 1/2 of its initial value is the constant and is known as the half value thickness, or HVT. The half value thickness x half is related to the linear absorption coefficient mu by the expression that x half into mu equals to ln 2. এই কোশ্চেনটা তোমরা জানো, এটা আমাদের ওই যে রেডিটিভিটি চ্যাপ্টারে আমরা বের করছিলাম যেটা কিভাবে হয়। সো বেসিক্যালি এখানে যদি আমরা i কে i0/2 লিখে দেই, তাহলে ইভেন্চুয়ালি এখান থেকে x এর ভ্যালু ইন টার্মস অফ মিউ কি আসবে, সেটা হচ্ছে এটা। সো আমরা আগে যেটা শিখছিলাম সেটা হচ্ছে যে ল্যামডা ইনটু লন ল্যামডা ইকুয়ালস টু lambda equals to ln 2 divided by t half. মনে আছে? For the radioactivity chapter, decay constant equals to ln 2 divided by half life. Anyone remember this? This was the half life and decay constant relating equation for the radioactivity chapter. Similar equation over here, x half into mu equals to ln 2. So basically the same thing. It can be useful for some sets of calculation, but this equation is not very popular in terms of problem solving. But it's not a bad thing that you know this thing, because it's pretty similar to stuff that you've learned earlier. So you have to know the equation, definition of the HVT thing, and eventually this last part that says that in practice, x half does not have a precise value, as it is constant only when the beam has photons of one energy only. So this means that x half, or the HVT thickness, is dependent upon two factors. It is because mu, the absorption coefficient, have a look. Mu is a constant of the medium that is dependent on the photon energy. So mu is a constant of the medium. This is for the X-ray beam, or also applicable, maybe somewhat applicable for the ultrasound as well. But here they're talking about the X-ray beam. The mu is the constant of the medium that is dependent on the photon energy, which means if you have different energy of the X-ray photon, you're going to have different values of mu for the same medium. Now, in an X-ray, we actually do have a range of energies, energetic photons that passes through. So that's why they are using this idea that in practice, x half does not have a precise value, as it is constant only when the beam has photons of only one energy. But that's not the case for X. So we have a range of energies that is sent through the patient's body. So HVT thickness is not a very precise value, but we can have somewhat of an understanding for a range of that, what is the typical value of this thing. The intensity of parallel beam of ultrasound passing through a medium also decreases exponentially with thickness. Thus, ultrasound has a linear absorption coefficient and half value thickness that is dependent on the medium, and is also known as the frequency of the, and also that depends on the medium and also the frequency of the ultrasound. Like I said, that it depends on two factors: that medium and the frequency of the wave. In this case, they said energy of the X-ray photon. Energy of the X-ray photon basically is E, which ultimately translates into the frequency of the X-ray wave, E equals to HF. So you know what I'm talking about, the Planck's equation. The intensity I decreases according to the expression I go to. The last thing that we have is MRI. MRI is actually pretty interesting. There is a significant amount of new stuff that you have to learn over here. And once again, I wouldn't be able to answer a lot of why questions, but I can tell you the parts that you are supposed to know for your syllabus, for the what questions and the how questions. So let me tell you this thing, that nuclei of certain atoms has a property called spin. The spin of a certain nuclei can have different axes for the same material within an object. The MRI actually stands for magnetic resonance imaging, which actually, when it was primarily developed, was named NMRI, which stands for Nuclear Magnetic Resonance Imaging. What happened is that because of the intrusive of the word nuclear, patients who would necessarily require, or the doctors who prescribe them to undergo an MRI diagnosis would not be very interested to do that diagnosis because the word nuclear is there, and generally it produces a bit of a scare in people's mind that nuclear is bad. We have stuff, nuclear stuffs are bad. So it was less popular. Exclusively to increase the popularity of MRI scanning process for business purposes and to increase the acceptance of the patient, they discarded the letter N. They discarded the letter nuclear. So now it's only called MRI, and apparently people are now sold off more about this, which is pretty weird, but works. So practically speaking, in the process of MRI, we're going to resonate a nucleus. This is the first thing that I want your heads to accept. In the process of MRI, we are going to resonate a nucleus, not atom, not electron, nucleus. To be able to resonate, it needs to have a frequency, because that's how resonance works. Whenever you provide an external vibration that matches with the natural frequency of an object, you have resonance. So this resonance that we're talking about for the nuclear magnetic NMRI or MRI is dependent upon the spin of the atom. Now, I want you kids to visualize something which can help you to understand this thing better. There are multiple different atoms for which the MRI can be done who have this spin property for the nucleus. For example, there are 3 specific elements which are mentioned in your syllabus. They are carbon, hydrogen, carbon, and phosphorus. These are the 3 elements which are mentioned. They have this spin property for the nucleus. But because of its abundance in the body tissues, hydrogen is the atom that is used in the scanning technique, because hydrogen is practically everywhere. It is the smallest in size in terms of atoms, except for helium. Helium is smaller than the hydrogen atom, but hydrogen is quite small, and hydrogen is everywhere. I mean, you think about it: water molecule, glucose molecule, DNA molecule. Hydrogen is everywhere, like everywhere. So it is abundant in the human body, except for places where it is not supposed to be. For example, if I give you a bit of an idea, if you think for the bone structure, the bone tissues, they are made with calcite cells, which stores a lot of calcium carbonate for the strength material in the bone. And the blood vessels do not run through the bones. The bone is basically a hollow structure, typically a hollow structure. So within this part, we don't have much hydrogen present. But if you think for the blood vessels, they're basically made up with water and plasma and everything. So they're going to have one type of hydrogen content. Then if you think for fat tissues, they're going to have another type of hydrogen content. If you think for muscles, they're going to have another type of hydrogen content. If you think for heart muscles, they're going to have a different value of hydrogen content. So different type of tissues has different level of hydrogen as percentage presence in their constituents. By locating the exact percentage of hydrogen molecule present in a certain location, we can precisely say what tissue is that, provided we have known values from earlier. I'll say this again. By determining precisely what percentage of hydrogen is located in a certain location in a human body, we can say what tissue is located in that location. So if we know the percentage presence of hydrogen in bone tissues, we know the typical value of this, and by somehow we can detect a certain part of our body has that concentration, a certain location, a 3-dimensional coordinate of inside a human body has that concentration of hydrogen. We can vice versa decide that, well, in that location we have some bones. Other than cutting open and looking at the bones, by that diagnostic process we can say that there are bones. If we can match the hydrogen concentration of muscles inside the human body by some mechanism to measure, and we can detect that the typical value of hydrogen concentration of muscle exists in some location inside the human body, we can say that that location of the human body has muscle tissues, and so on and so forth. You can go for a whole long list: muscles, tissues, and bloods, and plasma, and whatnot, fat. In the process of nuclear magnetic resonance imaging, or MRI, NMRI, we are going to practically find out the concentration of hydrogen nuclei. Important. Now you might wonder, hydrogen has one atom. One hydrogen atom has one hydrogen nucleus. So what's the difference in mentioning nuclei or or atom? I mean, what difference does it make? It does make a difference, because we are going to detect in this process the location of the hydrogen nuclei. We're not going to detect the location of a hydrogen atom. Well, locating a hydrogen atom essentially means locating the hydrogen nuclei, and vice versa. But then why is it so important for the words? Because this is essentially what is done, and this is essentially what is confused in the students, and that's what the examiners very precisely look for a level of correctness. Once again, we are detecting the location of hydrogen nuclei by the resonance mechanism. We are going to resonate the hydrogen nuclei, not the atom. Be careful about your wording. এটা আমি তোমাদের এখানে লিখেও দিছি এখানে কোজনে লিখছি এটা যে এখানে লিখে দিছি. Don't mess up words atoms or nucleus while writing or MRI. This is the most common mistake. এটা তোমরা যখন এক্সামিনেশন রিপোর্ট পড়ো তখন এটা পাবা. আচ্ছা, আজকে ফারিজা ক্লাস করতেছে না? Where is this kid? আচ্ছা, এরপর জিনিসটা হচ্ছে সেটা হচ্ছে যে আমরা কিভাবে কাজটা করব. Now, আচ্ছা, I was about to draw something. This class is gonna getting longer than 9:30, so please bear with me. I started a bit late, so I appreciate your patience. Hold your horses. Get yourself fed by your parents or your guardians. Let's say this is a hydrogen atom. Here is a nucleus. Figure not down to scale. This nucleus will have a certain spin. Think about the spin of the Earth. It has a spin, spins around the North Pole and South Pole axis. There are multiples. There are many. I mean, many of these hydrogen atoms. Let me just copy these things. Transparent selection. Copy. So I could do this maybe forever, still not represent even a small section of the human body. But let's say I'm only showing now here this much. So let's say we have a lot of hydrogen atoms